Okay, now we know the first law of thermodynamics, and we know that heat and work are the way you can get energy in and out of a system. What we're ready to look at now is quantifying heat. They don't very often just hand you heat on a silver platter and say Q equals, or say 5 kilojoules of heat was transferred in this reaction. Very often they'll make measurements that enable you to obtain the value of heat. So that's what this section is about. We'll eventually look at this equation, define the pieces and the parts of this equation. All right, so what is heat? We know this already. It's a transfer of thermal energy. I have mentioned the second statement there. It always goes from an object of high thermal energy, that would be higher temperature, molecules moving faster, to the lower thermal energy, typically a lower temperature, okay? And we a lot of times think about heat and temperature synonymously. They're not synonyms, okay, but they're related to each other. So temperature is a way that we measure that thermal energy, okay? We know that kinetic energy and temperature are directly proportional, so we can measure temperature and get an idea of what the kinetic energy is of an object. So the higher the temperature, the higher the thermal energy of that system because of the relationship between kinetic energy and temperature. So whenever we think of an object having a high temperature, okay, we say, oh, it's really hot, there's a lot of heat, but no. Heat is the transfer of thermal energy, and when we go outside and say there is, you know, it's really hot today, it's a lot of heat, okay, there's a lot of transfer of thermal energy from the surroundings to us, and that's how we interpret it. Okay, so some terms that go along with this. The first one is what's called specific heat capacity. Specific heat capacity is, there's a lot of different ways to abbreviate it, but in this textbook, they abbreviate it with a capital C sub S, and it's the amount of heat required, this is its definition, to raise 1 gram of an object by 1 degree Celsius. Okay, so let's just kind of envision. Let's envision a tiny little gram of water. Now, this is not obviously really water, and that's probably not a gram, but if this was from here to here a centimeter, okay, that would be 1 cubic centimeter. And if it's a cubic centimeter of water, it equals 1 gram because it has a density of 1 gram per cubic centimeter. So just imagine a sugar cube that's about the size of a cubic centimeter. And if you had that in water, that'd be a gram of water. And then we want to take that gram of water and we want to put a Bunsen burner under it and we want to heat it up. And we want to heat it up, let's say, from 25 degrees Celsius up to 26 degrees Celsius. I mean, you probably couldn't even tell the difference if you put your finger in it between those two temperatures. It's a very small increase in temperature. So imagine, do you think that this is a really, really a lot of energy or a little bit of energy? Whatever it is, it's specific to water. The amount of energy it takes to raise that little cube of water by 1 degree is different than if it were a cube of aluminum, which would be different than if it was a cube of alcohol, okay? Each substance has got its own specific heat, okay? And it's called its specific heat capacity. Now, these are the units that we have for specific heat capacity. This is not the only way it can be defined. So if you're reading through and doing a homework problem, maybe in our homework system, you might see other units, but this is the one that our book gives. You might see it in joules per gram Kelvin instead. That's okay. A change in temperature in Kelvin and a change in temperature in Celsius is the exact same magnitude. So these units and that unit would be exactly the same. You might see another common energy unit is calories. Okay, you might see this in calories or kilojoules. But as long as it's an energy unit, over mass times Kelvin. Now, I have also seen it. They're like, forget about it per gram. Let's do a specific heat capacity in an energy, and they use moles. I don't like it when they do that because in our definition of specific heat, it's defined by grams. But you could say, well, this is how much energy it takes to raise 1 mole of a substance by 1 degree Celsius. And that would be okay because it's an amount of energy, a quantity, and a temperature. For the most part, the units that we'll work with, certainly in class, will be these, and I just dropped my pen. Hold on. Okay. And we'll use these units, but if you're working through a problem and you see something like this, know that it shouldn't throw you off because our units are going to cancel. We work with them very carefully. Okay, the next thing is called heat capacity. Let's imagine for a minute that we don't just have 1 cubic centimeter or 1 gram of water. Let's have instead 2 grams of water, okay? And I still want to raise these 2 grams of water by 1 degree from 25 degrees Celsius, boy, I don't know what I'm doing there, up to 26 degrees Celsius. So I'm going to raise it up 1 degree. I've got twice as much. Would it not seem logical that if I had twice as much, it would take twice as much energy to raise it? So all you have to do to get heat capacity, and heat capacity is abbreviated with just a C there, is to take the mass you have times the specific heat, the amount of heat it took to raise 1 gram by 1 degree Celsius. So M times C sub S, or mass, times specific heat capacity will give me the plain old heat capacity. All right. Its units would certainly be joules per degree Celsius, because if I took, let's take this last one, joules per gram degree Celsius, and I multiply it by grams, wouldn't those cancel and be left with joules per degree Celsius? So it could be in joules per Kelvin. That would be fine. It wouldn't be numerically any different. And that's the typical units you'll see, though, is joules per degree Celsius. So it's taking into account the full amount that I have and how much it takes energy-wise to raise it by the 1 degree. What if we didn't want to raise it 1 degree? What if we wanted to raise it 2 degrees instead? Let's take this same object here and not go from 25 to 26, but go from 25 to 27. Would you imagine that it should take twice as much energy to raise it twice the temperature? Well, it does. And that gets us to our final equation. Our final equation for heat is the mass of the object times the specific heat capacity of the object times how much temperature change we're putting into that object. So if I have an object, if I have a substance, and I undergo a change in temperature, I can now know the amount of energy in heat it takes to raise it by that temperature. Now over on the right-hand side, there is a table from the textbook that gives the specific heat capacity of several different things. And you'll notice that it really changes from one to another. Up there we see lead at 0.128. It takes a tiny amount of thermal energy to raise 1 gram of lead by 1 degree Celsius. If I go and look at water, it's a pretty high heat capacity object. It takes 4.18 joules to raise it, a gram of an object of water, by 1 degree Celsius. We'll use that water one quite often. You'll get familiar with that 4.18 value there. But each object, what I really want you to get from this little discussion here, each substance has its own specific heat capacity, how much energy it takes to raise 1 gram of that substance by 1 degree Celsius. All right, so we see that delta again that we've introduced here. Delta means change. It's always final minus initial. It's very important that you put them in the right order so that if an object is getting, its temperature is rising, it's got a positive change. That means it's taking in thermal energy, and that will give you a positive heat. Bringing it in is a positive heat. If you did final minus initial and the object was cooling down, the temperature was decreasing, that would be a negative value for delta T. A negative value for delta T is going to give you a negative Q. That means the object is giving its thermal energy out to the surroundings. And so watching that, the order that you put your temperature in will be very important to get the right value for your Q. Okay. It is important that you realize that you don't have to do a unit conversion if you're given temperature change in Kelvin. Don't feel like you have to convert to Celsius, because the magnitude of change, if something changes by 5 degrees Celsius, it changes the exact same temperature, and it's changing by 5 Kelvin. That would not be true in Fahrenheit. You can't work in Fahrenheit here, but the change in temperature in Celsius and the change in temperature in Kelvin are the same magnitude. All right, so you're going to try one here. You're going to calculate the amount of heat liberated and you have 366 grams of mercury. It's cooling from 77 degrees Celsius down to 12 degrees Celsius, and you are coming up with a value for this Q. All right, stop, pick your one, and then resume. Okay, let's see, what did you choose? Did you choose B? If you chose B, then you did it correctly in the units that we're looking for. We're looking for units of kilojoules. Now if you got that and you feel comfortable with it, we're not completely done with this video, but you can kind of scoot ahead to the next problem. Otherwise, you might want to watch what I'm talking about here and make sure that you understand all the pieces. So Q equals mc sub s delta T. We look through and we see that the mass of the object is given. If you'll be really consistent to write your units, you'll realize that you need to do a unit conversion. The specific heat capacity is given to you as 0.139. And if you're working on a problem and it's not given to you in the problem, it's probably in that table that I showed you on the previous slide in your textbook, or you could do a quick web search for a specific heat capacity. Just be looking for the units you need there. And then the change of temperature. This is really the place that it can be messed up. It's the sign convention, but I didn't give you any positive values anyway. So we do final. This ended up at 12 degrees Celsius minus the initial, and it started off at 77, and that was 12.0. Let's sneak a 0 in there, okay? 12.0 degrees Celsius, it's final minus the initial. It started at 77.0 degrees Celsius. And let's look at our units. The grams are canceling. When I subtract these, I have Celsius, or a Celsius is canceling. I'm left with joules, but I don't want it in joules. The problem is asking me to provide it for them in kilojoules, and I know that a kilo means 1,000. So when I do all of that work, it is going to give me a negative sign because of this, and the value is going to be a negative 3.31 kilojoules. Okay, now sometimes we can't stick a thermometer in an object and measure its temperature change. Let's say we're dealing with that piece of metal that's in the flask, and I want to know its thermal energy change as it transfers energy to the water. I can't stick a thermometer inside of that piece of metal and measure how its energy is changing. But I can stick a thermometer in the water, and I can measure how the water. So anytime you have two objects touching each other, they're going to transfer thermal energy between them. And just like delta E, it works for Q. Whatever the system is doing, the surrounding is doing the exact same thing, but opposite in sign. If the system is giving off 5 joules, the surrounding is absorbing 5 joules. So we're going to be kind of doing a problem here and considering this transfer of thermal energy. So we have a problem here. It's a little bit more involved, a lot more words than our one we worked on before. We're going to at least get it set up and then have you finish it up. We have an object. It's a piece of unknown metal that we're dropping into water. It tells me the mass of the metal. It tells me the temperature it's starting with, and it's putting it into the water and tells me the temperature the water is starting out with. And it wants to figure out what the specific heat capacity of the unknown metal is. So let's work on setting this problem up here on the light board. The Q of the system is equal to the negative Q of the surroundings. I'm going to call the system the metal. It doesn't matter which one's which. I'm going to call it the metal, and I'm going to call the surroundings the water. Now let's finish by looking at that last sentence. Assume the metal and the water are isolated from everything else. What does that mean? That means no extra heat is going to leave outside of the water. We're going to assume that the transfer is just happening between those two things. It helps keep it simple. So what would we do? We'd take this beaker, we'd put it in a thermos of some sort to where the heat can't leave, at least in the duration of the transfer process. It'd be too slow to leave the energy of that container. Okay, so that's what that last sentence is saying. So now let's break these two pieces apart a little bit more. What do I know about the metal? I know that whatever the mass of the metal is, times the specific heat capacity of the metal, times the change in temperature of the metal, is equal to all of that for the water, but there's a negative sign there, so we got to make sure we don't drop that negative sign. Really easy to do. We have the mass of the water. We have the specific heat capacity of the water. And we have the change in temperature of the water. So those are all the pieces that we know. And let's go in and let's put the values that we know into there. The metal is 25.5 grams. All right, so that's what we have. The specific heat of the metal is what we don't know, and that's our unknown. So I'll just keep it as my symbol C sub S because I don't know it and I'm trying to find it. Change in temperature is final minus initial. Now it does not say specifically what the final temperature of the metal is. But if it's going to transfer the thermal energy, it's key to note that it's just going to transfer thermal energy until they're both the same temperature, and then there's no more transfer. So if the water went to a temperature of 27.45 degrees, then the metal also went to a temperature of 27.45 degrees. So that's the final temperature. They both go to the same final temperature, and that's always going to be the case if you wait long enough in a thermal transfer situation. Well, what temperature did it start out as? Well, let's see. It said it heated that metal up to 115 degrees Celsius before it submerged it. So that's the left-hand side of this equation. Now let's consider the right-hand side of this equation. I'm going to move it down to make sure that I have plenty of room, but the right-hand side, I don't lose that minus sign. Okay, so there it is. The water. How much water do I have? I have 101.5 grams. All right, so that's the mass of the water. The specific heat capacity of the water, well, I'd have to go to the tables and look that one up. It's 4.18 degrees joules per gram degrees Celsius. And its change in temperature, well, it also finished up at 27.45 degrees Celsius. It started out as 25.00. Okay? So there is everything filled in that I know from this problem, and it only has one unknown. The one unknown is this. Now that's algebra, and I think you all can handle the algebra. So I'm going to leave you with coming up with an answer for that and bringing that with you to our next class, and let's discuss it and work on other problems where there's different variables left out.